Your lecturer is Felix J. Lockman. Dr. Lockman is the Green Bank Telescope Principal Scientist at the Green Bank Observatory, a radio astronomy observatory that is a facility of the National Science Foundation. He received his PhD from the University of Massachusetts, Amherst. Dr. Lockman's area of research is the structure and evolution of the Milky Way and nearby galaxies, with a special emphasis on radio observations of neutral hydrogen. He has worked for many years at the National Radio Astronomy Observatory and regularly lectures to diverse audiences about radio astronomy.
Welcome to this course on radio astronomy. Now that's a peculiar phrase, radio astronomy. We all know what radios are. We listen to radios for the weather, news, sports, and music. And we all know that astronomy is the study of things out in space, like stars, planets, and comets. Astronomy is a very ancient science. What's it got to do with radios? That question, and some tantalizing hints from early experiments, led a couple of scientists back in 1955 to string thousands of feet of wire between poles on rented farmland outside Washington, D.C. They were after the steady hiss of radio waves given off by an exploding star far out in space, but they also got bursts of radio signals, kind of a cackle that seemed to be interfering with their research. At first they thought that the bursts might be coming from a farmer's noisy tractor ignition, but they detected it when all the farmers were in bed. Eventually, they realized it was coming from the planet Jupiter. Jupiter is the largest planet in the solar system, easily visible to the naked eye. When Galileo built his first telescope in the 1600s, one of the first objects he looked at was Jupiter, and he discovered that it had a number of moons revolving around it. They're easy to see through binoculars today, but the implications in the 1600s were profound. Worlds around worlds. So in 1955, about 350 years later, some sort of radio bursts from Jupiter were picked up by a couple of guys in a field outside Washington. Here's what they heard. Not very impressive, is it? But these are radio signals from another planet, natural radio signals. It made headlines in all the newspapers of the day. Since then, astronomers have made astounding discoveries about our universe by studying the natural radio signals given off by objects in space. Radio waves from familiar objects like the sun, moon, and planets. But radio waves from exotic objects as well. Exploding stars, vast clouds of organic molecules just a few degrees warmer than absolute zero, and even radio waves from the Big Bang that marked the beginning of our universe. In this course, we'll sample many topics from the vast field of radio astronomy. And to get started, let's look at the sky. Here's a picture of the sky. It's the sky over the Green Bank Observatory in a valley in West Virginia. You can see some of the big dishes that we use to study radio waves from the universe. But this is not the sky you see at night. What this picture shows is not the light that we would see with our eyes or regular telescopes that collect and analyze light. What we're looking at here is the sky that we would see if our eyes could detect radio waves. This is not the familiar night sky, it's the radio sky. And what are all these objects? These small bright spots and these strange blobs? Before we answer that question, let's talk about radio waves. What exactly are radio waves? And for that matter, what is light? You might be surprised to learn that radio waves are actually a form of light. No, to be more precise, a radio wave is exactly the same as light, just a different color, a very different color. What we call light is just one part of a continuous electromagnetic spectrum, distinguished by energy and wavelength. Light of different colors has different energy. For example, blue light has higher energy than yellow or red light, and red light has a longer wavelength than blue light. Radio waves are all the way over here on the left, the lowest energy light with the longest wavelength. Now, between radio and light is the infrared, the radiation that our skin feels as heat. And higher energy than light, we get ultraviolet radiation, the kind of light that can give us a sunburn. Radio, infrared, light, and ultraviolet are all forms of electromagnetic radiation that have been given different names. X-rays are here as well, at higher energies than the ultraviolet. Then gamma rays, just other forms of electromagnetic radiation, just other forms of light. So what's special about radio waves? Why could radio waves tell us something about the universe that we can't learn from light, or from infrared, or even X-rays? Well, there are at least 3 reasons why we study the radio waves from objects in space. The first reason is that there are things out there that just don't give off any light at all. They don't emit light. They don't reflect light, but they do give off radio waves. If we did not receive their radio waves, we wouldn't know about them at all. Here's a great example, a pulsar. A pulsar is what remains behind after a massive star ends its life in an enormous explosion. The pulsar is the remnant, and it's the densest known form of matter. Pulsars are called pulsars because their radio signals come as pulses. Blip, blip, blip. They were discovered because they emit regular pulses of radio waves, unlike any other object in nature. Now, when we think about radio, we think about radios and listening to sounds. Well, with pulsars, we can actually listen. We can take the output of a radio telescope and pipe it through a speaker and listen to the sounds of space. Here's how a pulsar sounds. By the way, let's look at the electromagnetic spectrum again and mark the signals that we just heard. These pulses were recorded at 327 megahertz, just there, a bit above the FM frequencies, but below digital television frequencies. We'll spend more time on pulsars later on, but I brought them up here because they're a great example of objects that give us lots of information through their radio waves and hardly any information from light. So that's the first reason for studying radio waves from space. There are objects out there that only make their presence known through their radio emission. The second reason why we might want to study radio waves is because they can go places that light just cannot. If you're at home, you can take your radio or your cell phone into a closet and it will keep working. The radio waves somehow come right through the walls of your house and even into a closed closet. Try that with light. This is important because out in interstellar space there are clouds of dusty gas. Pretty impressive, eh? Around the edges of the photograph, you can see countless stars, but in the middle, nothing. Like trying to look through a brick wall or your closet door. The dust in this interstellar cloud totally blocks the light from behind it. Clouds like this are common in the Milky Way, our home galaxy. So when we try to look through the Milky Way, the light is blocked by dust. See all those dark blotches running right up the spine of the Milky Way? Those are dark clouds, tens of thousands of dark clouds, and they block our view so thoroughly that looking with light, we can only see about 5% of the entire Milky Way. But just as radio waves come through the walls of our house, radio waves can pierce the dust and reveal what's behind those clouds. Even better, radio waves can sometimes tell us what's going on inside those dark clouds. You can hide from light, but not from radio waves. A third reason that radio astronomy is important is that it can be done from the ground. And by that, I mean that it can be done from the surface of the Earth. Now, we don't think about this too much, but besides supplying us with the air we breathe and the weather, the Earth's atmosphere acts as a kind of protective blanket around our planet. We know that on clear days, the atmosphere lets the sunlight through just fine. And even when it's cloudy, there's never any question of whether it's day or night. Some light comes through even when it's cloudy. The atmosphere is pretty transparent to light. But the atmosphere is not transparent to all parts of the electromagnetic spectrum. Let's take X-rays. The atmosphere is completely black to X-rays. They don't get through. This is actually extremely fortunate for those of us who live on Earth, because the sun gives off some pretty nasty X-rays, but they're blocked by the atmosphere and don't zap us. Let's hear it for the atmosphere. But the wall works both ways. At X-ray energies, the atmosphere keeps X-rays from coming through, absorbs them actually. But from the surface of the Earth, we can't look out at X-ray energies either. If we want to study X-rays from the universe, we have to put our telescopes into space, and that's expensive. The same is true for gamma rays, ultraviolet, and most of the infrared. A thick wall, a black sky. But not the radio. The atmosphere is transparent to radio waves, as well as normal light, and we can do radio astronomy from the ground. Very convenient. By the way, it's this property of the atmosphere that keeps the Earth warm at night. The atmosphere lets sunlight through, where it warms the Earth, but the radiation from the Earth that comes out in the infrared is trapped by the atmosphere and sent back. That's why it gets cooler at night in the mountains than in the lowlands, where there's less atmosphere, there's less trapping of the Earth's heat after the sun goes down. So we have three reasons to study the natural radio waves coming from space. One, they give us information we wouldn't otherwise get. Two, they can come through the dust. And three, we can do it from the ground without the expense of going into space. Let's take a few minutes now and cruise through some of the universe, looking at some objects, first in visible light, then in radio waves. We'll go into detail about these later, but for now, let's just sit back and enjoy the ride. Let's start by revisiting Jupiter. Here's a sketch of the solar system, and there is Jupiter. It's a gas giant planet, a lot farther out from the sun than the Earth is. Here's how Jupiter looks in visible light. Actually, Jupiter does not give off any light itself, but it reflects sunlight, and that's what we're seeing. Now, here's a radio image of Jupiter, and this is what we detect with a radio telescope. Pretty different, eh? With Jupiter, we are clearly detecting something in the radio that just does not give off light. And this means that we're learning something about Jupiter that we couldn't have learned from reflected sunlight alone. Now in this course, I'm going to be showing a lot of radio pictures. So let's take a few moments to talk about how we make pictures from radio waves. Now we could display the radio data on Jupiter as a bunch of numbers. After all, that's how we detect radio waves, by measuring the output of a receiver and turning that into a number or set of numbers. But where possible, we like to take advantage of the power of the human eye. After all, we humans are really good at recognizing patterns in pictures. So when possible, we turn the numbers that come out of a radio telescope into a picture of the intensity of radio waves, and we often color the pictures. Are the radio waves from Jupiter really red? No. Radio waves don't have color at all. But we color the radio images to make use of the power of our eyes to see patterns in colors. In this image, the brighter radio waves are colored red and the fainter ones are colored blue. It's an arbitrary color scale, but it helps us visualize the radio signals. Back to the universe. Let's look at something else. Here's a photo of the remnants of a star that blew itself to pieces about 1,000 years ago. Those little wisps are the only parts of it that are giving off light. Now let's look at the radio. Wow, what a difference. It even looks like the fireball of an explosion. About once every 100 years, give or take a bit, a star blows up like that, somewhere in the Milky Way. That's the death of a star. Let's now look at star birth. New stars are born all the time, made out of gas in dark clouds like the one I showed you earlier. Those clouds are black, absolutely impenetrable to light. But we can see into them with radio waves. There's a dark cloud in the middle of this figure. Now we add the radio emission. With radio waves, we can see those glowing filaments inside the dark cloud. That's where the gas cloud is collapsing to make new stars that make their own heat and light, like the sun. The sun was born in a place like this, and the Earth as well. Our next example is a galaxy, kind of like the Milky Way, but smaller. It's a collection of stars bound together by their own gravity. This photo shows the light from the stars. But galaxies have an extended atmosphere, just like the Earth does. Galaxies are not just stars, but they have some gas, sometimes dense gas clouds with dust, as we've seen for the Milky Way. The hydrogen in this gas, in this atmosphere of galaxies, gives off radio waves that we can measure. Here's what we see for our little friend. The hydrogen is colored blue. When I was an undergraduate, I had a job for several months each year as an assistant to a radio astronomer, Dr. Mort Roberts. And he was making some of the first maps of hydrogen around galaxies. And he was finding, as we shall see, that quite often the hydrogen atmosphere of a galaxy was much more extensive than the light, was much more extensive than the stars. Here's one of the figures that he was making at the time. The photo is reversed so that black shows the light from the stars in that galaxy, and the contours are tracking the radio emission from the hydrogen in that galaxy. See how much further out the hydrogen goes than the stars? As Roberts was finding hydrogen further and further out from the stars, a puzzle was growing. I was making these contour maps of hydrogen based on his measurements with radio telescopes, and he would say, "What's holding it all together?" You see, it was clear early on that there wasn't enough mass in the stars of some of these galaxies to keep the hydrogen gas from flying off into space. There wasn't enough normal matter. There wasn't enough gravity from the stars. And that was one of the major threads that led us to the concept of dark matter. Here are two more examples of what we learned from radio observations of galaxies. Here's a group of galaxies in a photograph showing the light from their stars. Most galaxies cluster in groups. Our Milky Way does as well. Here's a group with 5 galaxies, and the image shows their starlight. These galaxies look pretty normal and undisturbed, but wait till you see their hydrogen. The galaxies that look splendidly isolated are connected by bridges of hydrogen, torn out of their atmosphere as they whirl past each other. The hydrogen tracks where the galaxies were millions of years ago and lets us understand where they've been and where they're going. Kind of like a jet contrail, visible long after the jet has passed. Through the radio images made by measuring radio waves emitted by hydrogen, we can track the past motions of the galaxies in this system. Here's a final example, and a very different type of galaxy. The blue and white shows light from stars, and that fuzzy ball in the center is a galaxy. This is the kind of galaxy that we call an elliptical galaxy because instead of being shaped like a flattened disk, a pancake like the Milky Way, it's roundish. It also doesn't have all the dark clouds that the Milky Way has, though it does have some dust in the middle. Not too impressive, is it? But look at the radio waves shown in red. That galaxy is surrounded by 2 large lobes of radio-emitting stuff far out beyond the stars. Here's another elliptical galaxy and its radio waves. We see 2 huge plumes, or lobes of radio emission, emerging from jets that seem to shoot out from the very center of the galaxy. The stars in the galaxy aren't giving off radio waves, something else is. What an amazing structure. Finally, let's look at just the radio emission, not adding the light from the stars. This is one of the strongest radio sources in the sky, and you can clearly see 2 jets emanating from a central hotspot and feeding the large radio lobes. The power in these radio galaxies is enormous. They are some of the brightest objects in the universe. Every one of these galaxies has at its heart a black hole, an object so dense that even light cannot escape. It sucks up everything in its surroundings. But as stuff gets sucked down out of sight forever, some process, and we think it involves magnetic fields, takes some of the infalling matter and blasts it out in jets, moving near the speed of light. A spectacle of unimaginable energy and great beauty. These objects go by various names: quasars, active galactic nuclei, radio galaxies, and their true form is revealed only through their radio waves. It's time to end this brief tour of objects that we study in radio astronomy. We'll spend more time with each of them in coming lectures. But what I want to do now is show you some of the telescopes that scientists have built over the years to do the work of radio astronomy. What does it take to capture the radio waves from galaxies exploding at the edge of the universe? Well, despite the fact that we are looking at some of the most energetic events in the universe, they are so distant, so extremely distant, that by the time the radio waves reach Earth, the signals are extremely faint. From a purely abstract point of view, we can look at a telescope that collects radio waves as a funnel that just concentrates radio waves from a certain direction in the sky to a spot where we can put a receiver. It should be clear from the drawings that as far as collecting radio waves, it's not the depth of the funnel or its shape that matters, The amount of radio waves we collect depends on the size of the opening, the aperture, we call it. We measure the intensity of radio waves as the power that passes through an aperture of 1 square meter in 1 second in a bandwidth of 1 hertz. We measure the intensity of radio waves in units called Janskys, named after Carl G. Jansky, who first discovered radio waves from space. 1 Jansky has the value of 10 to the minus 26 watts per square meter per hertz. That's a very small amount of energy. 1/100th millionth of a billionth of a billionth of a watt per square meter per hertz. Now, a snowflake weighs about 1 milligram, and it falls at about 1 meter per second. So if we could harness its kinetic energy for 1 second, we'd get about 1 millionth of a watt. That puts our radio signals into perspective, doesn't it? And I can tell you that these days we are studying objects in the universe that are measured in millijanskys and microjanskys, 1,000,000 times weaker than a Jansky. Now, by comparison, your standard cell phone at a distance of about 1 kilometer puts out about 5 times 10 to the 15 Janskys. 5 million billion Janskys. That's 5 million billion times stronger than the signal we would get from a bright quasar. Now, I've just used some numbers that are very big and some that are very small. So it's time for a brief review of what we call scientific notation. In scientific notation, we express numbers as a power of 10 with a decimal number in front to show where within that power of 10 the number lies. Here is the decimal notation and scientific notation for several numbers. To put a big number into scientific notation, just shift the decimal point to the left and put as a power of 10 the number of places you've shifted it. For a number less than 1, shift the decimal point to the right and put the negative of the number of shifts in the exponent. Take the number 311,000. We shift the decimal point 1, 2, 3, 4, 5 places to the left, so it's written 3.11 times 10 to the 5th. For the number 3/1000ths, the decimal point is shifted 3 places to the right, so the exponent is negative. So 1 Jansky is 10 to the minus 26 watts per square meter per hertz. How do we detect such faint signals? We'll go into more detail in a later lecture, but one thing for sure is that we will want to have as many square meters as possible in our aperture. We want a big funnel. Also, most radio sources are fairly constant in time, so we can add their signals over many seconds, minutes, hours, sometimes even days and months. We also often average over many hertz of bandwidth, sometimes a megahertz or more. All this gives us a signal that we can measure with state-of-the-art receiving systems cooled to a temperature near absolute zero. But a large aperture comes first, and modern radio telescopes have apertures of thousands of square meters. Most radio telescopes these days, though not all, look like big dishes and are the equivalent of radio mirrors that gather the signals and bring them to a focus. Later on in the course, we'll take a tour of a major radio telescope up close. But for now, let's look at a gallery of radio telescopes from around the world to give you a flavor of the extraordinary technology that goes into these beautiful instruments. We'll also talk a little bit about why they are, where they are, and what they do. In a couple of words, radio telescopes collect radio waves and bring them to a focus where the waves are received and measured. The telescopes also have to point at different parts of the sky to track objects as they rise and set. The science of radio astronomy got going after World War II, when the technologies developed for the war effort were turned to peaceful uses. In the years 1955 to 1965, many nations around the world opened radio observatories and began exploring an invisible universe through this new window. Here's a gallery of some of the radio telescopes built during that era. This radio telescope is in a remote part of the Netherlands. It was completed in 1956. It's 25 meters in diameter and was designed to study the radio signals from hydrogen. For about a year, until the telescope at Jodrell Bank was finished, This was the largest radio telescope in the world. This was the first really big dish, at 250 feet in diameter, built in a field outside the village of Goustry in Cheshire, not far from Manchester, England, and completed in 1957. You can see that it rides around on a track and tilts up and down on those big gears in the middle. Part of this telescope was made using war surplus battleship gun turrets. Although it's 60 years old, this is still the third largest fully steerable radio telescope in the world. This 26-meter diameter telescope is at the Canadian Dominion Radio Astrophysical Observatory outside of Penticton, British Columbia, and went into operation in 1960. Radio astronomy was a thriving enterprise in Australia in the years after World War II, and this large dish, 210 feet in diameter, was completed in 1961. It's located near the town of Parkes, about 400 kilometers inland from Sydney. This telescope has an unusual design. The dish sits on a base that contains its control room and offices. The Parkes telescope was called into service to monitor communications when the first astronauts landed on the moon. A story told in the movie The Dish. When you visit, watch out for kangaroos. They're everywhere. We'll visit this radio telescope in Puerto Rico in a later lecture. It was dedicated in 1963 and for many years was operated by Cornell University. The 300-foot and 140-foot telescopes in Green Bank, West Virginia were put into operation in 1962 and 1965. They were the first large public radio telescopes in the United States. While we're looking at the 140-foot telescope at Green Bank, let's notice something about its location. We're familiar with large optical telescopes in their domes that are sited on remote mountain tops. Optical telescopes need to be away from city lights and at a high altitude to get above the clouds and to reduce the blurring of starlight by the atmosphere. But the radio telescopes are in a valley surrounded by mountains. Radio observatories aren't worried about light. Their enemy is interfering radio signals from man-made transmitters. The mountains provide shielding from distant radio transmitters, from TV stations, cell phone towers, and the like, that could interfere with the radio signals from space. So radio observatories are located as remotely as is practical, and where possible on valley floors shielded by mountains, just the opposite of optical telescopes. And although you can't see light from the stars on a cloudy night, lower frequency radio waves can come through even overcast skies. So countries like England, the Netherlands, France, and Germany, where there aren't a lot of good locations for optical telescopes, built radio observatories instead. Outside the village of Nancy, a 3-hour drive from Paris, the Nancy radio telescope was inaugurated in 1965 by Charles de Gaulle. Its design is unusual, with a large fixed reflector on the right and one that tilts on the left. This provides a lot of collecting area, but with reduced sky coverage. The signals from 3 60-foot diameter dishes outside Cambridge, England in 1964 were combined to form one telescope spread over a mile. During this period, there were many more radio telescopes built. Just in the United States alone, there were radio observatories run by Ohio State, Caltech, the University of California at Berkeley, MIT, the University of Illinois, Harvard, Cornell, and the University of Maryland. Radio telescopes can have a long lifetime. New discoveries are made continually, and many of the objects studied by scientists today were completely unknown when the telescopes were first built. So while some of the telescopes I just showed have been dismantled or decommissioned or used for other purposes, some are still on the front line of research. Radio astronomy is a vibrant activity worldwide. We've come a long way since we first gazed at this image of the radio sky hanging above the radio telescopes at Green Bank. And we know a lot more than when we began. What we see here in the radio sky are places where stars are being born and places where stars have died. And all those little points that look like stars are not stars at all. Every one of them is a galaxy with a monstrous black hole at its center, spitting out enormously bright jets of radio emission that we can see across the universe. This is our entry into the fascinating world of radio astronomy. Thank you.